A very good morning, afternoon, or evening to everyone watching this video. My name is Aditi Rajvaidya, and I'm an 11th grader studying in the Emerald Heights International School in Indore. Today, I will be presenting to you my research project, which revolves around windmills and what we can do to improve their efficiency. Let us start with a small introduction. What is wind energy? It is the electrical energy that is harnessed from the mechanical energy of the wind, and that happens through windmills. Let me break it down for you. Imagine there's a windmill in front of you, quite like the one I'm about to show you. Now, if there are fast winds, the blades of the windmill will turn. It is actually the kinetic energy, a type of mechanical energy of the wind, that causes these blades to rotate. All the blades of the windmill are connected to a rotor shaft. As the blades rotate, the rotor shaft also spins. This rotor shaft is connected to a gearbox, which is connected to a generator. The turning of the generator's rotor is actually what conducts electricity. Here, I will demonstrate for you a working conventional windmill. The LEDs will light up as energy is generated. Wasn't that fun? The following is a scary looking but actually a quite simple of a mathematical model of a conventional wind turbine. What we derive from all these equations is something called the Betz limit. The Betz limit's value is 0.59 for ideal conditions. The Betz limit says that no wind turbine can convert more than 59.3% of kinetic energy of the wind into the mechanical energy used for turning a rotor. This value is derived purely mathematically and in real life is only from about 0.35 to 0.45. In a nutshell, only about 10 to 30% of the mechanical power of the wind is actually converted into usable electricity. So, what must one do to improve this efficiency? This is where piezoelectric windmills come in, as an attempt to directly harness electrical energy from a windmill's blades and not just through the kinetic energy the blades collect from the wind. Now, what is a piezoelectric material? These are the materials that are capable of generating electricity when a mechanical force is applied on them. An example that I will be using throughout my paper is zinc oxide. For example, if you have a sheet of zinc oxide and you press it repeatedly, it will generate electricity repeatedly. Isn't that nice? Again, I have laid out another mathematical model for a piezoelectric windmill. In a nutshell, and through a lot of approximation, we obtain that the piezoelectric energy generated by zinc oxide is 300,000 joules. It changes with the voltage of the system. Now, there is a second sort of energy that is also generated when a piezoelectric material is used. It is called the piezo potential or the electrical displacement, and it leads to the generation of the 300,000 joule power that we talked about earlier. Let us imagine a zinc oxide crystal lattice. When an external force is applied to the zinc oxide crystal lattice, it causes a displacement of the positive and the negative charges, creating a dipole moment or a separation of electrical charges. The dipole moments generated in each part of the crystal lattice create an electric potential at the overall, that is, at the macroscopic level. This macroscopic electric potential due to the mechanical T formation is referred to as piezoelectric potential or simply piezo potential. This potential generated depends on the stress given by the wind and can be calculated using the formula dt plus epsilon naught E, where T is the mechanical stress Epsilon is a property of the material called the dielectric coefficient, and E is the electrical field applied to the material. The dielectric coefficient indicates how easily a material can become polarized under the influence of an applied electric field. Materials with a higher dielectric constant are more effective at storing electrical energy in an electric field. It lies between 8 to 10 for zinc oxide but can change with a variety of factors such as temperature, pressure, etc. In a nutshell, we got another type of energy that can be generated if the windmill is piezoelectric. But how can a windmill be piezoelectric? First, we construct the blades of the windmill entirely with zinc oxide. Next, we attach one wire to each blade. To prevent the tanglement of the wires during the rotation of the blades, we use a device called a slip ring. Now, piezoelectric materials generate alternating current, but the electricity that is of our use, such as that in batteries, runs on direct current, DC. So, we use a bridge rectifier to convert AC to DC. Next, we use a DC motor to generate electricity from normal mechanical energy. The DC output from the piezoelectric material, after being rectified by the bridge rectifier, is combined with the mechanical energy converted by the DC motor. Next, simply connect the free ends of the wire to the DC circuit after the bridge rectifier, finally integrating the piezoelectric effect into the overall electrical system. You can also connect an LED to the system just like I did. Most importantly, we have to understand that zinc oxide is a brittle material. Hence, we use epoxy resin to coat the blades, which also helps in attaching the wires to each blade. Although we do not have empirical data, through theory, we can still say that a piezoelectric windmill produces more energy than a conventional one, all for approximately the same price as calculated here. Thank you, and I hope this idea escapes the paper and is implemented in the world around us.